separating out the double and the singly unresolved limit. So I thought this morning a little bit of a maybe cleaner way of saying it. So for now, we'll just imagine that we have E plus E minus, so that we can ignore the beams just for simplicity, and we just have 3 partons, say, that are making a jet, just for our discussion. And then we would have P, let's say P1, P2, and P3 in our language. And they clustered, and we have some jet, one jet state that looks like this. Right? Now, the crucial point is that if I ever go to a double unresolved limit, so all the worst limits of QCD, or the really bad infrared mess, then I always get back to the leading order phase space. So my what have I got here? Let's just say 3, just think about it in the jets. This always gets mapped back to a single times some limit. So for example, in a collinear limit, we stick the 2 together to make a new parton that's going on shell, and then the soft one vanishes. So in the end, you just have this one left, which is your leading order phase space, right? So you always, in a double unresolved limit, always factor onto a single particle phase space, right? Because you lose 2, so 3, you have to get rid of 2, so you get back to a single particle phase space. And the single particle phase space always has that. So in a d phi 1, we always have tau 1 equals 0 because Q1 is equal to P1, right? If I'm just having a single particle phase space, then my parton is my jet, and P1 is equal to Q1, so my tau is just P1 dot Q1 over some scale, which is just 0. Yes?
Is the subscript on the tau the N in your N jettiness?
Yes, exactly, yeah.
So this is your one
This is my one jettiness, yeah.
Okay.
Yeah, exactly. Okay, so that's hopefully convinces you that in any double unresolved limit, it sits at tau 1 is equal to 0, as I was trying to explain yesterday. And that just you can think about it. You don't even have to worry about what the limit is. You can just think about it. It's always going to factorize onto something times a single particle phase space, and that's all that's important here. So that was the first part of our using it as a delta parameter in our slicing. The second part was that if it was non-zero, then we could only have at least one parton unresolved. So we never accidentally hit a limit where we have 2 partons unresolved. And that actually, you can use a similar argument as this one. So you say that you lose 1 particle, but now you always look at some 2 particle phase space. And so in your 2 particle phase space, you're always going to have, so you have Q1, but you're always going to have at least Alright, so you have something that looks like, this is the same Q scale down here. So you have, your tau always looks something like this, and you can, in a single particle limit, you can never kill both of these simultaneously, right? Because maybe, you could worry about a particle going soft that would kill 2 momentum, but there's always going to be some that survive. So you always have something which is non-zero. So in a single particle or a no unresolved limit, you always have at least one pairing that is that's non-zero to give you a non-zero value of tau. So anyway, so hopefully that was a similar way I was trying to explain yesterday, but hopefully that is a little bit clearer than some of the waffle I was giving you with these pictures. All right, so Q1 is determined by the hardest jet. So you have, so in this situation, we have a particle, at least have 2 that are going to be resolved and 1 that may be unresolved. So something like this, and it could be some wide angle soft. Now when this clusters, you're going to get at least 1 jet for it to be allowed. And it could be, either this one or both. But if it's both, I just take the hardest one. If it's just one, I just take that one. It's by definition the hardest one. Okay, so that's your question. All right, good. Okay, so hopefully that clears up some of the confusion from yesterday. Okay, so today we are going to look at doing a slightly different method that we can use to cancel the infrared singularities. That is a little bit neater in that it is numerically more stable. So we go back to our toy model to introduce it. So we had that our NLO correction in our toy model was written as VN. There's going to be no stupid calligraphic font in today's lecture, and hopefully never again. All right, so this was our toy model. Okay, and then when we went into the slicing, we just separated this integral into two parts, one near the origin and one away from the origin. And we had to make an approximation in defining our limit near the origin. So it'd be nice if we never had to do this. And again, I was having some discussion with people after the class yesterday when people were essentially inventing subtraction. They'd heard about, I showed you how rubbish slicing was, and then you quickly invented subtraction, which is clever. Well done, guys. So the point is that I would rather not do any approximation, right? So what I would like to do to sort out this real term is add in this. I'd like just to add this on, because that would be good for me, because then I could cancel the singularities in the real, which we'll see in a second, that it does. This, of course, is not cool, because I can't just add things to physics. It would be fun if we could, but physics is pretty tight about that one. So we can't just add in a random thing to our cross-section, so we have to add in and subtract it off again. So we're allowed to write the whole thing as follows. Let's see, I'll put the plus sign with this one. And then I have my real term. And I take it off again. Lovely. Do I need parentheses around the first two? I need a jet measurement on Vn, don't I? That will make you happier. All right, good. So I think only one mistake, so that's above average. Good. All right, so what I've done is it's effectively nothing. It's just an exercise in PR, which is a useful skill to have anyway in itself. I've literally just added something and taken it off. Really is absolutely nothing. But now I can start to do some magic. So this term here I can factor out. So I take out the jet function and do this integration here. And I get Vn over epsilon minus, plus, let me get my signs right, yeah, minus. From explicitly doing this integration, which I can do. Okay. And now over here, I can bring these guys under the same integrand. All right. And you guys are probably already smart enough to see that I'm done. This is going to be clearly finite. But as it's still early in the morning, we can go through the steps. So this thing here is effectively the first term in the Taylor series when I expand this guy around x is equal to 0. Right? Which was what I was effectively doing in approximate means before to get my subtraction. I was just doing it inclusively. Now I'm doing it under the integral. So when I Taylor series expand this, I get Rn to the x Fn plus 1 j to the x is going to be Rn 0 f nj of 0 plus d by dx of Rnx Fn plus 1 jx at x x is equal to 0 times x plus order x squared. All right, so when I do my Taylor series expansion, and then I use, again, implicitly my knowledge of jet safety, I can get rid of this f here and just make this into an fnj, which I'd have done. So this thing here, by using my infrared safe observable, is going to be the same thing as this thing here. And you see, so when I subtract this off, this bit cancels. Right? So this minus this will cancel this bit here, and I'm left just with something which goes like x. Well, lots of questions. Let's start from front to back.
So you're integrating till x equals 1, so don't you have to include like many orders, x squared and x cubed and so on?
Yes, but this is just, I'm not actually going to do this Taylor series. I'm just motivating that this thing is finite. I can repeat the question. The question was, I'm integrating over x, so isn't it my Taylor series naughty? He said it in a clever and more polite way. My counterpoint was that was an excellent point, but I'm not actually going to do the Taylor series. Right? That would be getting back to slicing. This is just an argument that this thing is finite as x goes to 0. Right? Because as x goes to 0, the limit is cancelled by this thing, and this thing is my first term. This gives me an x in the numerator, so this thing will scale like x minus epsilon, which I can just set epsilon to 0 and integrate. So that was the second question.
Yes, there's an fn plus 1 inside the integral. Wasn't that also an rn plus 1?
No, this was there was some debate about the subscript on the n. It was I think one of the highlights of yesterday's lecture. So n was designed in our toy model to be the number of particles in the leading order. And then in our toy model, we had one extra degree of freedom, which corresponds to x. So you would think that I would write Rn plus 1 to specify that it has an extra degree of freedom. But in my notation, that's implicitly assumed by the x dependence. So the x plus n is already n plus 1. So the f, yeah, because the f is a bit more, yeah. That's, yes, that is random. That's because physics sucks. However you think of a notation, it's always wrong, right? So yeah, this is really to highlight that it is a separate, that it really is a different function, right? So at least the r is different to v, so it's easy. But this thing is really to show you that it has a dependence on x and this. So yeah, it is a little bit excessive. I could have just kept fn and then have 0, but anyway, good. But it is very important that this measurement function exists, right? And that it has this correct limiting property. So if I didn't have that, if I had something which was explicitly depending, that this thing went to some different value, so it didn't hit the leading order one, then I would break physics, right? You see straight away it would be infinite. Right? This term wouldn't cancel with this term, and I wouldn't cancel with the virtual over here, and so I would be in a lot of trouble. Right? So this factorization is necessary. But the well-defined measurements in terms of an infrared safe observable is crucial to make reliable predictions. Yes?
How do you know, demonstrate, prove, whatever, that your FN is an infrared safe observable?
So for this toy model, there's no actual physics in the toy model because I haven't done anything, right? I've just given a few labels and said one of them has a singularity that looks like this, and one of them has a singularity which I integrate over some region and it sits at x is equal to 0. So in the toy model, it's completely arbitrary. Like my KLN theorem is merely that this is equal to this, which is not a huge theorem, right? But in real life, in real QCD, I can set up a system of constraints that any infrared safe observable must have. And it effectively was the same definition that we already wrote down, just with the more degrees of freedom, because we said that the limit as x goes to 0 of fn plus 1 j of x has to go back to the leading order definition, right? And that's effectively what you do in QCD, any infrared safe observable, but now you have to include your limits, include all unobserved limits. So anything which, when you lose 1 or 2 partons, factors back onto the same observable, get leading order, is going to be an infrared safe. It's sort of so you can sit through and check. There's a sort of algorithm which you can go through and check that you have to satisfy to conform to infrared safety. But it's effectively the spirit of this that you always factor onto the lower point, and then the lowest point is enough to ensure that the leading order is finite, and then you're good to go. All right. Any other questions? Okay. All right. So my claim now is that this second term is finite. So I just set epsilon goes to 0, and again we recall our KLN theorem from yesterday. It's really disservice to KLN, who worked hard on their actual. So our toy model is infrared finite if this is true. So there you go. Okay, so what's the big difference from subtraction and slicing, as you see from these toy model examples, is effectively that we don't make any approximation, because rather than doing something inclusively, like in slicing, where we just do the whole integral in some region of phase space, where we understand there's some factorization, we now just make a subtraction term that lives with the real integration in the real phase space. So we take we have some function that we invent, we put it in, and it cancels the singular limit. So for us, it's easy because in this toy model, there's only one parameter, so we only have to have one subtraction. But of course, in a real QCD calculation, we have multiple different potential infrared limits. So we have to have multiple different subtraction terms that get put in to cancel each sets of singularities that we can encounter. So in a real calculation, there's a lot more subtractions you have to worry about. So why is it better? So it's better because there's no approximation. This formula is exact. So that's nice. So I don't have to worry about some dependence on some parameter which is unphysical, which I then have to show doesn't affect my calculation. The complexity, the problem is that defining these things outside of a toy model can be quite tricky, and you have to be able to do two things. You have to be able to define it such that it works here, and you have to be able to do this integration over the unobserved degree of freedom explicitly. So you have to have something which is good enough that it is simple enough that you can integrate it, but also effective enough that it cancels the singularities. So defining these subtractions is the hardest part of the game here. And we'll look at an example at next leading order, so you can see you get a feeling for it. And at the next leading order, these subtractions are incredibly complicated, but they exist. So then the final reason why it's stable, so you might wonder that there's still a numerical instability here, right? Because this thing is in the region of x is equal to 0. These things are both large and cancelling. So you might worry that this thing is potentially numerically unstable. But because you can do it inside the same integration, you can just generate your integration variables accordingly. So you do this pointwise, and it is much more efficient to do it under the integral rather than globally as two inclusive numbers. So it works better numerically too. All right. So any more? Yes.
So in this example, the singularity in Vn is only 1 over epsilon.
Yes.
But in principle, you said there could be 1 over epsilon squared.
Yeah, or 1 over epsilon fourth, the next leading order. Yeah.
Yeah, but do we have some symmetry to cancel that divergence?
Let's do a real QCD calculation, and then you'll see. Okay. So that's an excellent segue into the next section, which is we'll do a simple calculation. I think the easiest one you could possibly do, and it still be real QCD. So we will do Higgs to BB bar next to leading order. So we have some Higgs that's decaying on shell to a bottom quarter pair. So we say at leading order we have the following. We'll call B1 plus B bar P2, and we have that 2P1 dot P2 is equal to m Higgs squared, which is a naughty way of hiding the fact that I'm neglecting the B quark mass, which is, of course, not cool, but yeah, it's the joy of being the one with the chalk. So I'm setting it the B quark mass kinematically equal to 0, but I'm keeping a non-zero Higgs-Yukawa coupling, so I actually have something to calculate. So okay, so that's okay for LHC kinematics, where we're going to make a very hard pair most of the time. You just have to be a little bit careful with some subtleties, but that's not what we're talking about now. So we're assuming that YB is not equal to 0, which is my Yukawa coupling. And then we have a process to calculate. So at leading order, there's just one diagram, which we squared it. And this is just a nice, simple constant for a non-shell Higgs. So you can see how this comes about pretty quickly. This is just some U bar and V, and then when I square it up, I get a trace over P1, P2, which then just gives me a S12 when I take the trace. And then that S12 is just m Higgs squared, which is this term here. There's a factor of NC from the number of color, and there's a factor of 2 if you do all your factors of 2 properly. Okay? Good. All right, nice and simple. All right, so this thing to get, this is the matrix element, and then to get something like a partial width, we'd have to integrate over the two-body phase space. which we'll write down in all its gory detail for a change. DDS. And then momentum conserving delta function with my factors of 2 pi to the d. Good. So I have massless phase space, momentum conservation. That's how I build my two-body phase space. Okay, so that's the leading order. And yeah, we could do this integration if we wanted to, but that's not really what we're after right now. So then we now worry about the next leading order. So in particular, because we're interested in seeing how these subtractions work, we're worried about the real matrix element. So we're interested in the process Higgs goes to B bar G. So in our notation, that's so I call the gluon P3. Very imaginative. Okay, so I need the matrix element. So now I have two diagrams. So it's twice as hard. So I have one where I radiate the gluon from P1, plus one where I radiate the gluon from okay. So again, these aren't particularly hard. We're not going to sit and do them. Of course, now I should, if there was a nice symmetry and completeness to these sets of lectures. If I was older and wiser, I would do this with amplitude so I could bring it back to where we started from. However, I'm not that old, and I'm getting older, but I'm definitely not that wise. So we just calculate the matrix element squared here in using traditional Feynman diagrams, because for a 3-point amplitude, there's really no difference in complexity. So we'll calculate this. We calculate it in regular Feynman diagrams, and to be super clever, we'll keep it at the full d dependence as well. So we'll make this d-dimensional.
Is there a reason you don't include the virtual correction?
Is there a reason? I'm going to include the virtual correction. It's two separate calculations, right? So if I didn't include the virtual calculation, then we'd have infinite as the answer. So we will in a bit, all in good time. Good. Okay, so that's our real matrix element squared. We call this M0 Higgs BBG squared. All right, and this thing will skip the actual calculation. We'll just give the answer. Alpha S on 2 pi is a factor of CF, which is CF is NC squared minus 1 over 2NC. It's a Casimir. All right, and then what do we get? We get NC and 2m Higgs squared y b squared, and then we get some dynamics. So we get something called PQ of x 1 over S13 plus 1 over S23. Okay, so we're recording that S13 is just Sij is just 2pi dot pj, and x is the S12 over m Higgs squared, and then this is the splitting function. In d dimensions. Averaged over spins. Good. Okay. So this is our matrix element squared. And what can we see? So we see that this thing here, this NC2m Higgs squared YB squared, is nothing other than our leading order. So I'm using one of my colored chalks. This is my artistic moment, so don't miss it this time. So I'm going to put going to highlight that. This is this chalk is insanely large. So this bit here, so this is what we're always going to factorize onto an infrared limit. And then this bit here is the dynamics, which is going to give us the infrared limit, the bits that set how we approach the limit. So for example, if we were to take the soft limit, so the soft limit is that S13 is equal to S23 is equal to 0. Right? This is when P3 goes to 0. You see both of these blow up. And further, X will go to 1 in the soft limit because S12 goes back to M Higgs squared in my leading order topology. So you see this term here also blows up. That's what gives me my 2 poles. And a collinear limit is one of them goes to 0. So in that case, this would remain finite, so we just drop it. This thing is blowing up, and it's multiplying the splitting function, which is, as we saw yesterday, controls how we approach the collinear factorization. So there's this times the expected splitting function. So this thing has the right structure to give us the infrared singularities we know and love. Happy? All right, good. So let's find some nice blackboards. Oh yeah, so now we have the matrix M. We need the equivalent of this phase space here. We need the 3-body phase space. So let's write that down. Sure. So if I kill both, so if S13 and S23, then what I'm doing is taking, so S13 is equal to 2P1.P3, and S23 is equal to P2.P3. Right? So if they both vanish, then P3 has to go to 0. Right? So that would be soft. And now in collinear, I have the configuration where this angle here is going to 0. Right? So then that tells me that P1 is parallel to P3. Right? And then this thing will vanish because it scales onto the light direction. This one stays non-zero. And then the other diagram would just correspond to the other collinear singularity where the gluon is radiated from P2. So there's 2 collinear singularities and then 1 soft singularity. Okay. All right. Okay. So where are we at to? 3-body phase space. All right. So our 3-body phase space is going to be a challenge to fit on the board, but give it a go. So let's be smart and save some room. We killed that down there. -1. All right, so that's my 3 massless phase spaces I have to integrate over. And then I have a momentum conservation between my final state. All right, so that wasn't too bad. Just got it on the board. Good. Okay, so that's okay. So now we have to invent some kind of dipole. So the complexity of these subtractions is that they're going to necessarily depend on the full real phase space because they have to have a dependence on the unresolved degrees of freedom. So in our example here, this meant they had to have an X dependence, which was trivial for us because it was so simple in our toy model. So they have to have in the subtraction term, which lives here, they have to have a dependence on the full 3-body phase space, right? But we have to have some way of mapping that 3-body phase space back to a 2-body phase space that corresponds to what we want to do over here when we integrate them, right? Because it's going to factorize onto our leading order phase space. So we have to have some way of mapping our 3-body phase space back to a 2-body phase space such that we can control the limits, right? And this is one of the complexities of making a subtraction that wasn't visible in our toy model. So we have to have some remapping. So what we have to do is map our set of P1 P2, P3 to some new phase space. So it's going to be a dipole that's going to depend on 1, 2, and 3. And then there's going to be some new two-body phase space, which depends on some different momentum, right? That's effectively what we have to work. We have to work out a mapping between these two phase spaces. So we can define this. This will be the phase space that lives in our integrated subtraction. So the implicit phase space that's in here. And the other term, and then this is the function that we want to integrate out to make our integrated dipole, and also our subtraction that goes into the real matrix element. Right? So that's a lot of words. So it's easier to see it with the equations. So the problems that we have to solve, that our map has to basically leave P1 and P2 on shell, and conserving momentum, right, to make it into a real leading order phase space. So that's what we have to do. So it's clear that we can't do anything with just 2 momentum, because if I try to do something with just 2, so I say I'm going to add 1 and 3 together and leave 2 alone, then 1, 3 will always have a mass, right? So I can't make the combined P1, 3 be light-like. So what I need to do to make a configuration with this mapping is I have to involve 3 particles. So I have to have something configuration like this. So this is just a general blob now, it doesn't have to be our process. So this is for any QCD process. I have a dipole that looks like this, and this is why they're called dipoles, right? So I'm going to have 2 particles that are involved in the limit. So they're called the emitter and the emitted. And then I have another particle that I'm going to bring into the dipole that is there specifically to ensure that I can conserve momentum and keep the remapped phase space here on shell, right? So that's diagrammatically what we want to do. So these were worked out by Catani and Seymour in the 90s, and their paper, you can look at all the different, there's different types of dipoles for initial state partons and final state partons, and different dipoles for quarks and gluons. So we'll just take the one we need. So this is the mapping that we need for the final. So we're looking at the 1, 3 case. So we're saying the gluon can either be soft or collinear to the first gluon. So there's this singularity, and then there's a soft singularity which lives in both. But S23 is not going to be going to 0 on its own. So then we have this P1 3 tilde, which is P1 plus P3 minus Y1 over P2. So in the language of the dipoles, this is the spectator, P2. Okay, now I want my P2 tilde to conserve momentum and still be light-like, so I can just make it into a simple rescaling of to absorb this. So I just rescale that P2, and I say 1 minus Y1 P2 mu. Okay, so now these things have nice properties that they conserve momentum. So P1 3 tilde plus P2 tilde is equal to P1 plus P2 plus P3. So momentum is still conserved, but now it's a 2-body phase space. And P1 3 squared and P2 squared can both be light-like. Right? They have to be light-like. I have to solve for Y1. Right? So P2 tilde squared is obviously going to be light-like because it's just a rescaling of a light-like direction. To make P1 3 be light-like, I have to solve for a specific value of Y1. Right? So Y1 is now predicted or fixed by the kinematics. So we can write that down. So if I choose this value of Y1, so S13 divided by the sum of the invariants, then my claim is that this direction here is light-like. So you square it and get 0. Good. So now we have the things that we need to make a dipole, because we can parameterize our we want to parameterize our dipole subtraction as the leading order matrix element in terms of these tilde variables, times some dipole function, which is going to cancel our singularities present in the matrix element over here. And then we can use that to locally kill all these terms here to make a finite function. And then we integrate it to cancel with the virtual, which was searched for earlier on. Clear? Unclear? Moderately clear. That's the silence of a moderately clear. After teaching undergrads, you learn to understand silences of like, that I have no idea what he's talking about versus I have some idea versus he's talking about such trivial things that I wish I was playing on Facebook. All right. So what we'll do is define the dipole from Catani and Seymour, and then we will add it to our matrix element and see that we get something that's finite. So the nice thing for us is that leading order is a constant, so the dependence on the p tildes is completely trivial, right? This thing here is just p13 tilde dot p2 tilde times 2, right? So that's a trivial dependence there, and so that bit's easy. So we only have to really worry about the dipole function. So from now I'm going to be extremely sloppy with my overall normalization, because following all the factors of pi's and 2's in this business is an irritation best not done in the lecture. So we're going to work in units where this thing is basically 1, so we're working in units of the leading order, and we're also going to implicitly subtract out an alpha s over 2 pi over cf. So we're effectively going to work in units of this and keep this, right? So that our matrix element is now just this divergent term here. So I think I call this, I call it calligraphic what was I thinking? Right. Let's call this, we just call it R, right? Yeah, that's not coming up anywhere else in this part. So this bit here, I can use another bit of chalk. This is going to be very colourful. Let's go for green. So this bit here, I'm calling this R. And that's all the divergence is, so I just want to sort this bit out, and then I've just factored out all of this guff over here. All right, so in those units, my dipole term, I call it D13, 2, so say who the emitter and the emitted is, and who the spectator is. So this is taken straight from the final section of Catani-Seymour's paper. So this is a man-made function. It has it wasn't derived from first principles. It was just constructed such that it had the right factorization properties that were desired. We already know what y1 is. That's defined upstairs. So we just have to define z1. And that's defined as s12 divided by s23 plus s12. Okay. So now, my claim is that if I take R, which is, so close. This isn't called R. This is just the thing that we want to, I'm calling it something different, sorry. We basically work in units of this. Yeah. This is the bit we keep. And I just suppress the dependence on this. Now what I call R is the combined green blob plus these dipoles plus the other dipole.
What did you break it down in green underneath that circle bit?
I think smudge technically,
Okay.
but it was meant to say keep. That's my laboured point was that I only want to keep this bit because that's where all the dynamics is, and this is just notation that I'll screw up. Right? It's just a normalization. So there's an arbitrary normalization that I don't care about, and this is the thing I do care about. Okay, and if I have to keep writing it, I will just go insane. All right, so now my matrix element, my real matrix element that survived in these units is given by this, plus D132 plus D231, right? So there's a second dipole, which I just get everywhere by swapping 1 and 2. So Z1 goes to Z2. You see this thing is invariant, but this thing down here changes to an S13. This one up here becomes an S23 over m Higgs squared, but that should hopefully a simple enough swap. So this is D132 with 1 and 2 swapped. Okie dokie. All right, now my claim is that this function here is finite. So I have to simplify it and show you the new function, and then maybe we can argue whether or not we believe it's finite. So this, of course, so you see that there's not any complexity here to do, because I know everything in terms of S13, S23, and S12 and m Higgs squared. So I can put this in. So remember, this was a function of S12 divided by m Higgs squared. So I can put all this in. I can put all this in terms of my known z's and y's, and then I can just ask Mathematica to simplify it for me. Go have a coffee, come back and see if it's done it. And if it hasn't, go have another coffee and do full simplify. All right. So that's tips from the professor. All right. So we want to. All right. So we basically. I was breathing some chalk then. That was a bad idea. Chalk does not taste nice. All right. There we go. It's better. All right. So if you do that, I think I only had to have one coffee. I think Mathematica got it on simplify. You get this function here. So this 1 minus epsilon is surviving from the epsilon dependence of this thing, which is over here, and there's an epsilon dependence there. And then I get the following. S12 times S12 plus m Higgs squared times S12 plus S13, S12 plus S23, m Higgs squared. All right, good. So my claim is that this function here is finite in any limit that I want to take. Right? And such bold, ambitious statements should be checked. So we can do that. So we have to check that if either or both of our S13 or S23 vanishes, then we're safe. But that's not too hard to see. So for example, if I take a single limit, for example, S13 goes to 0, then my R is a function of, so I just kill S13 in here, and I get an S12 in the numerator. S12 plus m Higgs squared. And then this thing just gives me an S12, which cancels this thing. This thing gives me an S12 plus S23. And then there's an m Higgs squared still. All right, there's no problems there. It's not blowing up. It's just a finite function. That's good. All right, and now if we want to set both to 0, so we take the soft limit where we do S13 and S12. Oh, sorry, S23 go to 0. Then what do we get? So we get S12 divided by S12 m Higgs squared. So we get 1 over S12. And then we get an m Higgs squared. All right, now you may worry that this thing has a problem when S12 goes to 0. Right? You may worry about that. It depends how anxious of a group you are. I think you're fairly laid back, so you're probably not too worried. Why shouldn't we worry about that? Yeah, you can't do that. That would just be insane. One has to have control when taking limits. You can't just set everything to 0 just for the hell of it. So we can't take that limit because there's a Higgs there, right? So if we can't have S12 goes to 0 at the same time as S23 and S13. We can make S12 be 0 kinematically, but there's no divergence or any physics in the matrix element. So it's basically So it's we can put it in as a parameter equal to 0, but in this limit S12 has to equal m Higgs squared, and then we just see that we just get 2 m Higgs squared divided by m Higgs to the 4th, so we just get a constant. So there is no dynamics in that limit. Okay, good. All right, so that's how this term up here is working, which I cleverly left alone. So in our full QCD calculation, we have 2 dipoles for this process. Of course, as we add in more complicated final states, we're going to get more dipoles. So if we had 4 partons, we'd have more dipoles to accommodate with the additional singularities. But we saw that the subtraction so the complicated bit was defining a mapping and then having this function. And then once we had the function, it was easy to make something which is finite and easy to integrate. So now what we have to do then to finish the calculation is to show that we can integrate the dipoles too, and that they cancel the virtual singularities. So that's also a little bit tricky notationally. So did I erase my 3-body phase space? I bet I did. Yeah, it's gone. All right, that would have been a nice equation to still have. It's still there. Perfect. Sometimes I win. There we go. Today's going to be a good day. All right, so we want to integrate the dipoles now. So we're living in this phase space, but what we want to do is map this phase space in terms of our tilde variables, such that we have the phase space that corresponds to an unresolved particle, and we can integrate over, times the 2-body phase space, which I definitely must have erased by now. That can't have survived that long. But the 2-body phase space is quite simple, so we don't worry too much about that. So what we want to do is to factorize this general phase space here, written here, into a 2-body phase space for the lower order, which depends on P13 tilde, P2 tilde. So we want this thing to be our leading order phase space, which would then live with our measurement function here. And then times some emitted phase space dpi, which is going to depend also still on the tilde variables. So you see it's one horrible exercise in Jacobians and delta functions. So our dipole depends on z and y, and we can see by looking at y and z that they go between 0 and 1. So the maximum you can make, say for example, z is survived here, right? So you see that if the maximum I can make it be is 1 if I kill S23, and I can make it be 0 at least formally by setting S12 to 0 for a general process. For our Higgs that won't happen, but in principle it could be 0. So z and y both range between 0 and 1. And so the trick that we do after many Jacobian identities is to repackage this whole thing in terms of integrations over z and y, right? And then because they run between 0 and 1, they're going to look like lots of beta function integrals that we can do. So getting this factorization isn't that bad because we have momentum conservation. So when we put in P1 plus P2 plus P3, we get P13 tilde plus P2 tilde. So that thing there looks a lot like the 2-body phase space kinematically. And so then we just have to, you have to basically work out the Jacobian transformation to go from this to this. That is definitely not something you do on the blackboard. So I'll give you the final answer. I'll keep this stuff for now. Yeah. Oh, I want that virgin blackboard up there, can I? Oh, no, I think it's good. All right. So if you have a rainy afternoon, you can do this exercise, and you will see that the emitted phase space for our process looks as follows. And 0 is less than or equal to z, 1 is less than or equal to 1, and y1. So I could have put these in as theta functions to make it look even more horrendous, but now I'm just going to let you know this is the limits of integration. Okay? Good. Good. This is the solid angle in d dimensions. So this is defined. The integration over it is 2 pi divided by pi epsilon 1 minus gamma 1 minus epsilon. We recall that d is 4 minus 2 epsilon, in case we forgot. All right. So now we have an integrand that we can do. So we have our function here, which I managed to not erase. I'm on good form. So d13 is our function we're going to integrate over this phase space. So again, it's going to be quite a caffeinated day because we plug that into Mathematica. We just do integrate now. Probably not full simplify because we want to graduate at some point, right? So you put it into Mathematica, let it integrate away, or your favorite integrating software, and we get the following. So we do. So we have to remember there's the. No, I've got the S13 in there. Okay, that's good. So I have to write S13 in terms of y and z as well. So there's a y dependence up there that's been a bit hidden. But we remember that was just S13 over m Higgs squared, so that's not too bad. So in the end, after integrating this up, we get that. So I will call this. Let's see. I'm not calling it calligraphic, Mr. Notes. I'm calling it. Let's call it d tilde. So this d tilde is the integration dpi d132. Right? It's my integrated dipole. Okay, lots of rage. Yes.
So, let's say if we want to put a scale dependence.
Oh, scale. Yeah, good man. So the scale I've throughout this whole calculation, I'm quietly sweeping under the rug that I'm doing this. But of course, you can reinsert the scales everywhere by ensuring everything has the correct dimensionality.
Like now this is fixed now. If you want to make
So they will.
something like that.
So you can of course always vary the scales by using the RGs, but for us in these things just enter in. You can actually quickly work out any missing scale based on dimensionality, right? So we're going to certainly have a mu squared to epsilon to make friends with this one over here, right? So they're implicitly factored out. Part of the mess that just makes writing these things on the blackboard a tedious task. But yeah, implicitly everywhere I'm going to be using this for the rest of the day to avoid complexities. But good question, good spot too. Any other related rage? No? So we're integrating this over the phase space. We plug and chug into Mathematica. We hope for the best. We wander off, come back in a few hours later, and we get the following. So again, I'm going to suppress some normalization factors. But in my units of alpha s over 2 pi cf times the leading order. So in these units here, my dipole term, I'm going to have to erase it now. Goodbye Arts equation, you were probably the most beautiful equation I've ever wrote on the board. All right. So our integrated term, so yeah, I should put a label on this so we remember which one it is. Is, again, there's a lot of prefactors I've sucked out, which don't add anything to the discussion. So really this should more be a proportional to 1 minus 3 epsilon all right, so that's integrating out. At least that's the important bit. There's some, as I say, normalization, which I've dropped. Okay, so what do we see? We see that it has 2 poles, as expected. So I can expand this whole thing in a series at epsilon. So this is exact in d dimensions. Now if I expand it, I get 1 over epsilon squared plus 3 over 2 epsilon plus 5 minus pi squared over 2 plus order epsilon. All right, so what I see is that I'm getting 1 over epsilon squared and then a 3 over 2 epsilon, right, which is parameterizing my infrared divergences. And the nice thing is that the symmetry in 1 and 2 is just going to be complete trivia here. I'm just going to get the same thing twice. So I have a candidate expression for what has to go to bed with my virtual calculation, right? So I say that the poles that I've integrated from my infrared subtractions go like now 2 over epsilon squared plus 3 over epsilon plus this, right, finite bit. Happy? Okay, so then we get our toolbox out, and there was the righteous indignation that we were ignoring the virtual over there, which was completely correct. So now we fix that issue, and we calculate the virtual very quickly, as we're about to run out of time. All right, so the virtual is just going to be given by a single diagram again, interfered with the leading order, squared. I want twice the real part of this. Anyway, this thing here, we'll call it V. And in our units of alpha s on 2 pi cf times the leading order, we get something which goes like B21, 4 divided by D minus 4 plus D. All right, so this B21 is the bubble function that we had previously. Right? And you see this doesn't look at all like the basis I was promising before, because if you get n different calculations, you can have n different bases. In our old style, in our style that we would have talked about yesterday, in terms of writing things in one loop, this d minus 4 is actually 1 over epsilon that would transform this bubble into a triangle, and we'd have a triangle coefficient times 4, which is good, and then we would have a pure bubble bit, which is this d, the 4 part of this times the bubble, and we'd have a rational part, which is the minus epsilon part of here times the epsilon part of the bubble. Yes.
I'm a little confused. So you put the cut diagram there, so it seems like you already squared something up.
Yes, so I want the whole virtual, right? So that I want the virtual matrix element, right? So there's an amplitude, and then I just times it by the leading order.
When you already said, then you already squared it.
Yeah, sorry, you're right. Over squaring. It's a bit like oversharing, but with a Q. All right. Yeah, good spot. I nearly got away with it. All right, so this is the bubble integral, which is given by the following. All right, and now we can happily subband this, and we can check. So we get the joyous revelation moment. There we get V is minus 2 over epsilon squared plus pi squared over 6 minus 2 plus order epsilon. This is interfering with that. Make it down here. So this looks like an epic disaster, which is how I'm just going to drop the chalk and walk away. Yeah, because when we add, so we're going to add V, which is this thing here, to our integrated dipoles times 2, because there's 2 lots of them. So we see the total, which is given by V plus D132 tilde times 2, is 3 over epsilon minus 5 pi squared over 6 plus 8. Uh-oh. All right, have fun. See you later, guys. So it's still broken, right? Well, at least still infinite. So what have we screwed up? No, that was yesterday's screw up. I like to do different screw ups on different days of the week. I find it keeps me leaner and happier. Any other screw ups that we could do? You want me to renormalize something? Yeah, it is a UV divergence, yes, but what UV divergence? So you want me to replace alpha s? Yeah, it's leading order in alpha s, right? So there's no renormalization beyond there, and we'd also have an F dependence, right? Because it would look like the beta function. So what's left? If I can't renormalize alpha S, I better renormalize something. Not the Higgs mass. YB. Why not? Yes, so we have to renormalize the Yukawa coupling here, right? It's not protected by the water density in the same way that it would be for your usual vector current. So it needs renormalization. And for us, well, you can already predict what the pole's going to be because physics works. But for our order, we need YB bare is rewritten in terms of YB renormalized 1 minus alpha S over 4 pi CF over 3 epsilon. Oops, sorry, over epsilon times 3. That's better. And then plus higher orders. Good. So now we're looking good. There's a 3 over epsilon. There's a 3 over epsilon here. So it looks like my job is done, apart from the fact that I erased everything. But here you say I had alpha S over 2 pi times CF. So there appears to be a missing factor of 2. Right? But we don't even have to worry about that because remember that we have YB squared. So when we expand it out to order alpha S, we're going to get a factor of 2 from the squaring that cancels the missing factor of 2 there. And lo and behold, this is in the MS bar scheme, of course. So lo and behold, then the poles cancel and we get left over just a finite bit. Physics works. Good, so then in the end, our renormalized correction scale is like 8 minus 5 pi squared divided by 6. All right, good, so any questions?
Really dumb.
Oh, perfect, that's my favorite.
If you square that, there's a 1 over epsilon. Why is there no 1 over epsilon squared?
There is, but that goes like alpha S squared, which I would have to then include at next and next linear order. That's not a dumb question. Any other questions? Yes?
So why haven't we looked at the self-energy corrections?
So you want like on the like here?
Yeah.
Because I like an easy life, and so I made these legs light-like, so there is no self-energy corrections. They're massless. So if I was a bolder and more ambitious physicist, I would have made P1 squared BMB, and I would have to also renormalize the bottom quad mass, right? Good. Any other questions? All right. So okay, so we basically come to the end of perturbation theory. It's done now. Life is easy. So I've tried to give you a little bit of overview of the things that you need to use as practitioners that you don't really typically get covered in traditional graduate lectures. So we went over on-shell methods, unitarity cutting, and how we solve the coefficients of these base integrals at one loop. And we went through infrared subtractions and phase-space slicing. We talked a bit about how it works at NNO. So I should advertise my friends that do subtraction at NNLO. So these things are much more complicated to do. I mean, you saw already it was getting pretty horrendous to write these things on the board at NLO. At NNLO, you have to do this twice, so you get just a horrendous phase space to integrate over, and it took a good, it took people's careers to do these calculations. So they started seriously working on this in, I would say, around 2005, 2006, and then the results have been coming out over the last few years. So sort of as a 10-year project to specify all these subtractions and then integrate them analytically to obtain the integrated subtractions. So it's a tremendous amount of work, right? So that was why I remember I said there was one advantage of phase-space slicing is that it was doable, right? Because there you just have to type in a formula and have a factorization theorem, which you get from some knowledge of physics. But then at least you're good to go, right? You have this unphysical dependence, but you can calculate. You at least can do things quickly. So those calculations have been done now, and the method is working. So I talked a little bit about NLO, and of course that's the frontier now. So we can do. The situation is that we can do anything we want at NLO now. We have these subtraction terms we looked at are completely process independent. You have to worry a little bit about managing the color, but it's certainly a well understood problem. So leading order, next leading order essentially solve problems in any field theory you like, especially relevant for LHC physics. And then the frontier is currently at n-NLO and n cubed LO, for which for n squared LO, for n2 LO, we have essentially an ability to do 2 to 2. So we can do pretty much any process that is underlying dynamics of a 2 to 2 scattering. So things like dye jets, Z plus jet, Higgs plus jets, that sort of thing, TT bar production. All those things we can, not every single 2 to 2, but most 2 to 2 are known. And then 2 to 3 is the frontier. So there's currently no n NLO prediction for any 2 to 3 process that really has a sort of pentagon-style 2-loop piece. And that's mostly at the moment now due to going back to the integrals. So we have to be able to do these Feynman integrals, so 2 loops, so this sort of thing. And this is where the bottleneck currently is. So there's a lot of work currently in the field on doing these. And if I had another 5 lectures to give, that's what I would talk about. And then beyond that, people started to think about how to handle infrared singularities at higher orders. So going up to things like n cubed or low, which you've already seen is necessary for the Higgs. But the prediction that we saw there was inclusive. So you don't get any differential information about the properties of the Higgs, but you get just the total rate at n cubed or low. So people are now starting to develop equivalent ideas for this slicing, and maybe, so slicing is often the first thing when you want to go for, because as I said, it was doable. So there's some developments there too. That's basically where the frontiers of perturbation theory are for the LHC, and things that some of you guys in the room can enjoy working on. So I guess before I go, I have just about time to squeeze in my rant. So I have my rant slide here. So you're probably too young now, sadly, to remember the Higgs boson discovery so many years ago. So many years ago. So the Higgs boson discovery is like one of the worst days of my life, I have to say. Really miserable about the whole thing. So it was the 4th of July, which is the Independence Day. So it was a holiday. And the Higgs, they announced at 9 a.m. CERN time, so you had to get up, stay away. You didn't go to bed, of course. You had to stay up to 2 or 3 in the morning to listen to a physics seminar, which was a unique experience. So that sucked. Having to get up stupidly early in the morning. Well, be awake stupidly in the morning. And then, you attend it, and the Higgs discovered, yeah, great, all that sort of stuff. Then you go on the New York Times website, and this was the front page of the New York Times website. And so it said there, scientists at the Fermilab in Batavia, Illinois, because they couldn't bother to pay to fly them to CERN, so they sent it to Fermilab as the cheapest option. So anyway, so they watched us having the seminar, and this was on the front page. And remember, this is at 2 or 3 in the morning. So this is this guy here, this old dude, should definitely be sitting back in his seat. And if he was sitting back in his seat, then I would have been famous, because that's me. So it's the most. I've known 6, 7 long years, however many long years have gone by, and I'm not over it. So I'm hunting for this guy. I don't even know who he is, but I assume that they waited, because I must have been sitting there and they just thought we can't put that on the front page of the New York Times. So we have to wait for this chap to obscure him. So anyway, so that's why it was a very bitter day for me, because it was nice to see in the Higgs and all, but that would have been a real moment of a lifetime to even one of my friends went, "Oh, go to the New York Times webpage. I'm right on the front page." And anyway, so I'm not over it. You never get over these things. Some of the scars never heal. But hopefully you guys are never traumatized in the same way as me. And then you can have long and happy, productive lives. And so I guess I want to wish you all the best for your remaining TASI. And you seem like a group, and I'm sure you'll have a great time. And see you around. Cheers.